From the time the first electric light bulb was invented by Joseph Wilson Swan in England in 1878 until 1931, electric lamps in Australia were imported. In 1929, 4 of the world's major lamp manufacturers decided to share the heavy capital expenditure needed to set up a manufacturing enterprise for making electric lamps in the relatively small market of Australia, with just 7 million people. Holding most of the various patents between them, they formed an association, setting up a new company that they called Electric Lamp Manufacturers Australia, Proprietary Limited. They were the British Thomson Houston Company of England with a 23.5% share, the Phillips Glow Lamp and Fabricant Company of the Netherlands with a 47% share, Siemens Lamp and Supplies Limited of Germany with a 6% share, and the General Electric Company of England with a 23.5% share. In 1929, they purchased 7 acres of land in Clyde Street, Hamilton, Newcastle, New South Wales for £85,000. Construction of the factory commenced in October 1930. It was completed in November, and the Phillips lamp assembly machinery was installed during February 1931 at a cost of £95,000. The company was registered on the 19th of March 1931. Production commenced with the filaments being imported from Belgium and the glass bulbs from Holland. The outbreak of war saw the establishment of a subsidiary company on the site in 1940, the Newcastle Glass Works. Cheap imports by the millennium heralded the closure of the ELMA factory, and on the 24th of April 2002, after 71 years of operation, production ceased. This documentary of the factory in operation, just before its closure, was recorded by volunteers from the Tamworth Power Station Museum. Making an incandescent electric lamp requires the use of 25 different elements and compounds. These may be broadly classified as glasses, ceramics, metals, and gases and vapours. The ores containing these elements and compounds each have first to be mined, and the elements extracted and refined to produce these high quality materials before successful lamp making can even begin. Commercial quality glass is not good enough for electric lamps. The requirements are stringent. For electric lamps, the glass must be perfectly homogeneous. It must not vary from batch to batch. Electrical resistivity, dielectric constant, and dielectric loss must also be satisfactory. The glass must have a resistance to chemical attack. It must also be readily workable and weldable in the sealing region, and its temperature coefficient of expansion must match the metal lead-in wire over a wide temperature range. And of course, it should be inexpensive to manufacture. The bulbs are made from soda-lime silicate glass, which is 73% silica, 15% soda ash, 7% lime, 3% magnesia, 1% potash, and 1% alumina. The stems are made from lead alkali silicate glass, which is 56% silica, 30% lead oxide, 8% potash, 5% soda ash, and 1% alumina. These quality raw materials are sourced and stored ready for use at the glass making furnace. These tubs containing the glass making ingredients of silica, soda ash, potash, lime, alumina, magnesia and lead oxide are awaiting elevation to the raw materials bunker above the glass furnace in preparation for weighing, mixing and charging into the glass furnace. These refined raw materials are discharged from the storage bunkers above the glass furnace. They are accurately weighed introduced into the mixing vessel, timed to ensure a thoroughly homogeneous mix. This mix is then fed into the glass furnace's continuous batch charger, where the melt becomes homogeneous at a temperature of 1400 degrees centigrade. Molten glass is easily contaminated, absorbing and attacking most materials it contacts, so careful selection of the internal sides of the mixing tanks, the fire bricks of the glass furnace and of the reheating furnaces is essential. The glass making process operates 24 hours a day, 7 days a week. An on-site laboratory monitors and controls the glass composition, making daily adjustments to keep the glass coefficient of expansion and its softening points to precise specifications. At a temperature of 1480 degrees centigrade, the molten glass becomes homogeneous and flows to these reheating furnaces above multi-position pneumatically operated bulb blowing carousels mounted with 16 perpendicular blowing heads. Each blowing head receives a measured drop of molten glass from the feeder furnace, fed down through an orifice into a fall pipe, as each blowing head passes beneath the fall pipe. Compressed air blows this lump of molten glass into the blowing head while it revolves about its perpendicular axis. As the carousel progresses step by step around its 16 positions, the glass begins to take shape, and the outer split moulds waiting in readiness to close around the roughly shaped bulb. The outer split moulds are dampened with water before closing around the glass, and compressed air blows the glass fully into the damp mould. The steam produced provides a cushion for the glass against the steel mould, cooling the glass and giving the bulbs their high degree of polish. These machines are blowing bulbs at the rate of 4,800 per hour. That's 80 a minute. A modern Corning ribbon bulb blowing machine can blow 50,000 per hour, 10 times this rate. The bulbs formed have an extended neck to facilitate assembly of the stems. These cooling bulbs are being discharged onto a conveyor belt to the stress-relieving annealing furnace. These glass-blowing carousels produce solidified bulbs with an extended neck. At the last rotary position, the split moulds open, releasing the solidified bulb, which is then partially cooled with a blast of air as it is ejected onto a conveyor belt. This conveyor belt takes the bulbs to the glass-fired annealing furnace, which reheats them to 400 degrees centigrade and then allows them to cool at a steady controlled rate to room temperature. The bulbs are spread across the conveyor belt before entering the annealing furnace to accommodate the faster arriving bulbs onto the slower moving furnace conveyor. This annealing process relieves the stresses in the glass resulting from the moulding process. The bulbs are taken by this conveyor to an inspector, where each and every bulb is inspected for flaws in the glass. This inspector is viewing each bulb as it comes before him into a background of monochromatic yellow light, passing through the glass from a high-pressure sodium vapour lamp. This highlights cracks, uneven glass thickness, and retains stresses not removed by the annealing process. Flawed bulbs are discarded from the conveyor and returned to the glass furnace as cullet for remelting. Bulbs which have passed the inspection for flaws in the glass are placed in a hopper for conveyance to the pearling process, where they are loaded onto a carousel. Here, the bottom of the extended neck is softened and reformed. The bulbs are then sprayed internally with hydrofluoric acid as a first treatment. This etches the internal surface and roughens it with thousands of minute prisms which refract the light rays in a myriad of directions, concealing the filament and diffusing the light without materially affecting the overall light output. In turn, each bulb is then drained, rinsed and resprayed with a treating acid to toughen the glass, which has been made brittle by the etching acid. The bulbs are again drained, flushed out with water to remove all traces of the etching and treating acids, and then dried. Alternatively, the bulbs may be charged electrostatically and sprayed internally with a fine silica powder dissolved in an adhesive binder, which is then set fast with heat. The bulbs are then placed one by one onto a conveyor, where they pass by a machine which trims the purling back from the neck, where the welding to the stem will take place. The bulbs leaving the purling process are then conveyed by an elevator to the lamp assembly machinery on the floor above. The stem tube, exhaust tube and filament support cane rod are made from lead alkali silicate glass as three separate glass components, which are then welded together. Lead alkali silicate glass is used for internal lamp parts because of its higher electrical resistivity, which prevents electrolysis occurring at the pinch seal. The four-part lead-in wires are fabricated on machines which weld the nickel filament support wire to the Dumet composite wire, Dumet meaning two metals, and that to the thin copper fuse wire and the copper connecting wire to the cap terminal. These are welded using a hydrogen reducing flame. The same machine flattens the top end of the nickel filament support wire and bends it over into a small hook, ready to receive the end of the filament. Precision manufacture of Dumet wire is crucial to the success of the lamp. This wire must have the same temperature coefficient of expansion as the glass at the pinch for the bulb to remain hermetically sealed over the lamp's wide operating temperature range. Dumet wire is drawn oversize from an alloy of 57% iron and 43% nickel before being heavily electroplated with copper to form a sheath. This sheath makes up 30% of the total weight of the plated wire, with the overall diameter about 8 millimeters. This composite wire is then drawn down to size below 0.8 millimeters through a series of dies, annealing taking place between drawings. The wire is then passed through an oxidizing furnace and through a solution of sodium borate to coat it with a flux of borax. This facilitates a close connection with the hot glass. The cut stem tubes are fed into this flare-forming carousel. Here, the bottom ends are heated with carefully controlled LP gas jets while they are kept rotating. When the glass has softened, a profiling finger, rotating in the opposite direction, flares out the soft glass, ready for welding onto the neck of the bulb. The four components that make up the stem are fed from hoppers into a machine where opposing gas jets heat the top of the stem tube until it collapses around the Dumet section of the four-part lead-in wires. A small clamp squeezes this portion together to pinch the glass to the wires to effect an airtight seal. The top end of the exhaust tube and the bottom end of the filament support cane rod are heated and welded to the top of the stem tube pinch. At this same time, while the glass is still soft, a puff of air is directed through the exhaust tube to blow a hole in the side of the pinch to connect the exhaust tube with the interior of the bulb. The completed stem assemblies are loaded onto a multi-position carousel for fitting the filaments and the final assembly of the lamp. The manufacture of tungsten filaments was always undertaken overseas, notably in Belgium. This is a complex process, transforming the mined tungsten ores through concentration, chemical purification, physical metallurgical heat treatments to stringent specifications. This must all take place before a wire can be drawn down to between 50 and 15 thousandths of a millimetre in diameter for use in most common lamps. The filament wire is wound on mandrels, either as a single coil or as a coiled coil, to extremely close dimensional tolerances before being cut to length and finally annealed ready for assembly in the lamp. The prefabricated filaments are fed from a shaker tray to a pickup tray, from which pneumatic fingers place them, one at a time, onto a grooved drum. As each fabricated glass stem on the carousel stops briefly, pneumatic fingers pick up a filament from the drum and place it over the top of the glass cane rod, with each end up against the nickel filament support wire, just under the formed hook, which is then squeezed closed, crimping the wire firmly and providing the electrical contact. The fitted tungsten filament is then dipped into a solution rich in finely divided phosphorus in suspension to work as a getter, to remove residual impurities, particularly water vapour, traces of which remain on the surfaces of the glass and metals. This also includes oxygen, which is dissolved in the tungsten and is released when the metal is first heated towards its operating temperature. Water vapour decomposes into hydrogen and oxygen, where reaction with the phosphorus at elevated temperatures renders harmless these and other active elements. The next position, the filament supports and filament are moved away from the glass cane. The top end of the cane is softened with an LP gas flame, and the glass stud is press-formed on its end. At the next position of the carousel, the molybdenum support wires are inserted while the hot glass is still soft. Several positions later, when the glass has cooled to become firm, the filament support wires and the filament are moved back into their final positions, and the ends of the molybdenum support wires are wrapped as a single loop around the filament. At subsequent positions of this carousel, the necks of the glass bulbs are lowered over the filament assembly to place it in its final position within the bulb. While rotating, LP gas jets fuse the neck of the bulb to the flared edge of the stem tube, being careful to avoid excessive strain on the glass. The bottom portion of the neck, no longer needed, is cut off while hot and discarded as cullet to return to the glass furnace. While heated to drive out moisture, the bulbs have the air extracted to the highest commercially obtainable vacuum, as any trace of oxygen remaining would combine with the hot incandescent filament to produce tungstic oxide, reducing the thickness of the filament wire and volatilizing it to condense on the interior of the bulb as a yellowish white film. When the vacuum pumps have lowered the bulb pressure to 100,000th of a millimetre of mercury, a gas mixture of 85% argon and 15% nitrogen, which has been dried so that absolutely no moisture whatsoever is present, is introduced into the bulb. While still hot, this is immediately flushed out, the bulb re-evacuated, quickly cooled and refilled with gas. Quick cooling is essential to achieve the highest possible gas pressure, about 700 millimetres of mercury, or 92% of atmospheric pressure. After the gas filling, the excess length of the exhaust tube is heated, pinched, sealed and cut off with a small gas flame. As this conveyor progresses, it pauses briefly, while each bulb is stamped with a hot etch burnt onto the top of the bulb, showing the brand, voltage, wattage, country of manufacture and the production date code. The stresses set up in the bulb by the branding process are relieved by this gentle flame line. The caps are made from soft sheet brass or aluminium suitable for deep drawing. They are stamped out of the sheet with a single stroke into a die to the standard dimensions. The holes for fixing the two retaining pins are punched in the cap side. The brass sole plates are also stamped out together with the small hole to take the end of the lead-in wire. Although fitting the caps is a relatively minor mechanical operation, it is nevertheless important because, if faulty, it can cause much annoyance as well as danger. The cap must be able to withstand a torsion of 2.8 Newton meters, so the cement and its adhesion to the cap and the glass must be of a high standard to withstand the continual rapid heating and cooling when in use, including in hot environments such as boiler room. The cement comprises a mixture of marble dust, shellac, pine resin, chalk, malachite, glyptol and alcohol, which is applied as a paste to the metal cap and the glass and fused with heat at 230 degrees centigrade on this carousel. Alternatively, a proprietary thermosetting cement may be used. The brass sole plates are then fitted with the lead-in copper wires passing through the central hole. The two retaining pins are inserted into the cap sides. This assembly is fixed in position with black vitrite, low thermal expansion, low melting point glass. Vitrite is a plastic glass containing a high proportion of lead for fluidity and manganese to make it black. The brass sole plates are preheated for soldering to the wires with drops of lead tin solder to the design profile for the lamp connection required for standard spring-loaded lamp holder contacts. When the lamp is first switched on, heating the filament to 2500 degrees centigrade for the first time, dissolved oxygen in the tungsten and other occluded gases dissolved in the metals is released, which reacts with the phosphorus coating due to its preferential affinity, thus protecting the tungsten filament. This may be seen as a brief puff of white smoke during the first instant of the lamp's illumination. Any lamp which fails is ejected at the next rotary position. After gas filling and flashing, every lamp is individually tested. An energised high-frequency probe is brought to each lamp, passing a discharge through the lamp, where the colour of the resulting glow indicates the presence or absence of impurities. The lamps are then switched on to full voltage as a test at full brilliance. Light cardboard boxes supplied in flat packs by external contractors are loaded onto a machine which opens them into shape for insertion of the lamps. As the open boxes pass this carousel, the finished and tested lamps are placed into the boxes, alternatively cap up and cap down, so that when plastic shrink wrapped in bundles of 10, the bulbs are always next to caps, giving them resistance to breakage during handling and transport. The bulbs are pushed down into the boxes, which are then closed. The boxes are then counted. The boxed bulbs are stacked in packets of 10 and plastic shrink wrapped. The packets of 10 are boxed in cartons of 10 making 100 lamps in a carton. The lids are folded over, an adhesive tape seal applied, and a package label fitted to the cartons, which are then delivered to the dispatch store for shipping to customers. The on-site photometric laboratory tests samples of the production lamps for luminous output. They also test production batch samples of incandescent lamps for service life and maintenance of luminous output over life, which is 1,000 hours in accordance with Australian standard AS 2325/1993 tungsten filament lamps for general lighting service. Glass for tubular fluorescent lamps is soda lime silicate glass, which is 73% silica, 15% soda ash, 7% lime, 3% magnesia, 1% potash and 1% alumina. The glass, with a viscosity of thick hot treacle, flows from the furnace at a controlled rate onto the top of an inclined, rotating, hollow refractory mandrel. Air blown down the centre of this mandrel forms the red-hot soft glass at 800 degrees centigrade into a tube, which is drawn by a drawing tractor 25 metres away at a rate of 100 to 120 metres per minute onto a cooling conveyor. The size of the tube drawn is determined by the diameter of the mandrel, the draw speed, the rate of blowing air, the glass temperature and the rate of cooling. The hot soft tube, now cooled down to 300 degrees centigrade, is supported by carbon rollers and a cushion of air as it is drawn by this drawing tractor along the cooling race, passing through a gas-fired annealing heater to reduce cooling stresses before being cut into lengths. Tubing is cut to length using what is known as a crack-off stone, which is a rotating, water-cooled ceramic block, about 12 millimetres square, with a ground edge which barely touches the glass as it rotates around the tube. This is enough to create a thin line of rapid cooler temperature, where the thermal shrinkage shock produces enough stress to break the glass. The cut lengths are ejected onto an exiting conveyor to have the tube ends formed. The cut tubing exiting conveyor carries the tubes up to a horizontally revolving carousel, where the ends are softened with a gas flame and moulded to form a shoulder for fitting the end mounts and caps. The completed tubes have their formed ends annealed to relieve residual stresses in a gentle gas flame and are conveyed to where they are inspected for flaws. The cut tubes from the annealing furnace are fed onto an inspection rack above a monochromatic yellow high-pressure sodium vapour light. An inspector views the tubes against this yellow background light, which reveals any residual stresses in the glass. Flawed tubes are discarded and returned to the glass furnace as cullet. Tubes passing inspection are boxed to go to the machines which clean and coat them internally with the halo phosphate fluorescing powders. Random samples are taken and tested for length to close tolerances. Prior to coating the internal surface of the tubes with the halo phosphate fluorescing powders, the tubes are placed in vertical racks where they are washed with deionised hot water to remove dust, then dried and internally coated with a solution which seals the glass surface and dries to a thin, clear finish in preparation for introducing the fluorescent phosphor mix. The light output colour of a lamp is determined by the mix of fluorescent powders. The original zinc beryllium silicate manganese tungstate phosphor of 1931 replaced with improved calcium halophosphates in 1942, were themselves replaced by today's trichromatic phosphors of 1971. These are a mix of barium aluminate, which produces blue, calcium tungstate and lanthanum phosphate, producing green, and yttrium oxide, producing orange-red. The mix ratio of these phosphors determines whether a lamp becomes a white deluxe, a cool white deluxe, or a daylight deluxe. Mixing is undertaken in vats with measured quantities of the powders suspended in a solution of butyl acetate as a carrier and nitrocellulose as a binder. The tubes are coated internally with the fluorescent phosphor mix, to which has been added a lycra adhesive so that it will stick to the glass. The phosphor-coated tubes are heated in a drying cabinet to 600 degrees centigrade to burn off the lycra, which, if left there, would prevent the through passage of the light generated. In a separate process, the machines form the glass mounts, which provide the exhaust tube and a coiled tungsten heater element and its connecting wires. This heating element is coated with a mixture of barium, strontium and calcium oxides to promote thermionic emission when hot during starting. When the flared end of the mount is welded to each tube end, this seals the tube. One end mount also holds the small glass capsule containing the 1.7 milligrams of mercury required to provide the mercury vapour to work the lamp. After the mounts are welded to seal the tubes, they are evacuated through the exhaust tube in the mount. To assist with starting, a small quantity of argon gas is introduced at the very low pressure of about 3 torricelli, which is just 0.4% of atmospheric pressure, and the exhaust tube sealed off with a gas flame. The glass mercury capsule is then cracked to release the mercury. The end connection caps are threaded over the heater and electrode wires, which are then soldered to the lamp's electrical connection spigots that will fit into the standard lamp holders. Caps are cemented to the glass using a proprietary brand thermosetting cement, which cures in 15 seconds at 300 degrees centigrade. A higher than rated voltage is applied to initiate the first test light-up, after which the finished lamps are packed for dispatch. Batch samples of fluorescent lamps are laboratory tested for service life and maintenance of luminous output over life. Production at the time of closure in April 2002 was 1 million lamps per week. The lamp making machinery was dismantled, the incandescent machinery shipped to Indonesia, while the fluorescent lamp making machinery was shipped to India. By July 2002, the building was empty.